If I'm not recording, let me know. Or if I'm still going on and I'm not really talking about the specific parts of the notes, just tell me that I'm still recording and I'll pause. We're talking about trig relationships. There are two that we already know. We're lucky in MathSL that we only focus on 2 trig identities. Well, this being our big one. Sine squared theta plus cosine squared theta, I should have a theta, is equal to 1. And also that tangent is equal to sine theta over cosine theta. Now, the other thing, sine squared theta equals and cosine squared theta equals, that's just rearranging that first identity. Now, there are other identities that have to do with your reciprocal trig functions, which we'll talk about. But in SL, we are not going to cover those. In HL and in an AP Calculus class, you would, but not in Mathematics SL. So, to get what sine squared equals, you just simply subtract cosine squared from your top equation, that identity in red. And then the same is true for cosine squared theta. Now, the reason that we look at those rearrangements is because in a trig proof, you're going to need to rearrange your formulas sometimes in order to prove what they're asking you to prove. Okay, now where do these things come from? They come from a basic right triangle. Because on our unit circle, we can create right triangles and come up with all of those radian values. So I'm just going to label a right triangle. So if you have a right triangle, you know the Pythagorean theorem can be derived from that. So in other words, you know that a squared plus b squared is equal to c squared. Now, if we happen to divide everything by c squared, we actually end up with our identity. You can divide everything by c squared. When you start manipulating the Pythagorean theorem, then you start coming up with these trig identities. Well, a squared over c squared, if you're looking at a squared over c squared from angle A, that's opposite over hypotenuse, which is sine theta, right? Sine, that's sine a squared. And with b squared over c squared, if we're looking from angle A, that's adjacent over hypotenuse, which is cosine. So that's where we get the cosine a squared is equal to 1. Does that make sense? So that's, in its most basic form, how we come up with those identities, and they prove to be very useful in trigonometry. Now, I'm just going to mention your reciprocal trig functions. Like I said, you're lucky in that you don't have to work much with them in the SL syllabus, so if it's not on the syllabus, I wouldn't worry about it. But it is worth mentioning, right? So we have to understand, and I've stressed this with my 9th graders when I went over a little bit of the unit circle with them, there is a difference between an arc cosine and a reciprocal of the cosine function, right? Reciprocal is just flipping it, right? Putting it over, putting it underneath 1, right? Whereas an arc is actually what we refer to as an inverse, where your domain and range are switched around, and it you can graph it such that if you graphed cosine and arc cosine, they would be reflected over the line y equals x, right? So that's what the arc cosine is. Now, reciprocal functions, there are 3 of them: secant, cosecant, and cotangent. Secant is not 1 over sine, it's 1 over cosine. Actually, I find that easier to remember because what I think is not what it is. So secant is actually 1 over cosine, so it's the reciprocal of cosine. Cosecant is the reciprocal of sine, and cotangent is the reciprocal of tangent. On occasion, those will be important when you are working with trig identities, but not often for Math SL. But important enough to at least mention. Do we have any questions? Now the fun thing about these is when you simplify, it's really just factoring problems like we've done before with substituting sine or cosine for x and then factoring it and solving it. When you prove a trigonometric function, you are just getting your left side to look like your right side, which proofs we need a little bit more practice on, but once you get used to the idea, it's really not that bad. So this first one says simplify. You would treat it like you would any simplification problem with a quadratic or with a linear function where you get out your greatest common factor, which we have a greatest common factor of 2 here. So you can go ahead and take that out. At this point, you look back and you say, okay, well, how can I reduce 1 minus sine squared theta? Is there something that can be simplified into? What is that?
Cosine.
Yeah, cosine. Cosine squared theta. So this is really 2 times cosine squared theta. So the question usually becomes, how far do I go? Well, my answer to that is, if you can rearrange your expression such that 1 minus sine squared theta or 1 minus cosine squared theta can be simplified as sine squared or cosine squared, do that. Okay? If you can't go anywhere with it, then you can't go anywhere with it. But if it boils down to one of these relationships, then you want to show that. The next one, what can I take out? What's your GCF for B? Yeah, sine theta. So this is nice. You can take out a sine theta. You're left with the cosine squared theta plus a sine squared theta. And what does that reduce to? Cosine squared theta plus sine squared theta is 1. So this is really just sine theta times 1, which is just sine theta. Does that make sense? So not that bad. Expanding requires you to know those basic algebraic expansions. So a minus b squared is a squared minus 2ab plus b squared. You need to know that in order to expand this, which at this level, everyone in here knows, I hope. So you're going to square that first one. You're going to multiply and double to get the middle. And you're going to square the last one. Now, is there anything I can do with that? Or is it completely simplified? Yeah.
Can you change cos squared theta plus sine squared theta to 1?
Yes. The cosine squared theta and the sine squared theta, those make a 1. So you end up with 1 minus 2 cosine theta sine theta. Don't forget that if it's a difference of 2 squares, the rules in algebra still apply to these problems. You have 2 things, a cosine and a sine, being squared. And we know that if we have a difference of 2 squares, it's just their square roots added and subtracted, right? So that's what we're going to be doing. So this really factors to be cosine x plus sine x times cosine x minus sine x. And that's from a rule that we knew from algebra. Questions? Does that make sense? Okay, next one. A little bit more challenging. Well, right away, I know I can factor out the numerator, so I'm going to start there. I suggest that on these, just start somewhere. If it leads you to nowhere, bridge to nowhere, then just try a different method. Maybe try rewriting cosine squared theta into 1 minus sine squared theta, or try rewriting your tangent into sine and cosine over cosine. It just depends on where you're going. So I'm going to try this out and see if it takes me anywhere. For A, I'm going to factor out a 2. I get 1 minus cosine squared theta over 1 plus. Cosine theta. Now, the temptation is to look at this and say, okay, well, anytime I see a 1 minus cosine squared theta, I'm going to just change that to sine squared theta. However, if you change it to sine squared theta, you can't really do anything. You can maybe make a tangent. Nope, you can't do anything because you have the plus sign, right? So you can't even make a tangent there. So what's another strategy I could do? Because if I make it a sine squared theta, I go nowhere. Any thoughts? Well, if you're stuck, go back to algebra. Say, okay, I don't know what I have to do here, but what if it was 2 times 1 minus x squared over 1 plus x? Is there any way I could factor that? Well, is 1 a perfect square? Yes, exactly. So this can be reduced to 2 times 1 plus x times 1 minus x over 1 plus x, right? And then that would cancel those out. Well, that means that in the same way, you can change the top one into 2 times 1 minus cosine theta times 1 plus cosine theta over 1 plus cosine theta. You can cancel out this same expression in the numerator and denominator, and you end up with 2 times 1 minus cosine theta, which is 2 minus 2 cosine theta. Either one is acceptable. Questions? All right. So, how do I proceed with B? So let me get a different colored pen here. So for B, looking at this, cosine theta minus sine theta over cosine squared theta minus sine squared theta. Where would you start?
Is there any point in expanding?
Well, you can definitely do something with that denominator. What will that simplify to? Go ahead. Yep. Yeah, it is that a squared minus b squared. So you can take that denominator, make it cosine theta minus sine theta times cosine theta. Oops, shouldn't be squared. should be a theta, times cosine theta plus sine theta. And on top you have your cosine theta minus sine theta. Those cancel out. 1 over cosine theta plus sine theta. Now there is nothing you can do when you have an operation like addition and subtraction in your denominator. You can't split up the fraction, so you're forced to just leave it. Now, if it were in the numerator, of course, you could split things up and see if you could simplify further, but it's not in the numerator, so we cannot do that. Questions? Yeah. For this one, number 6, we're skipping number 5. Because it wants us to solve here, we have to not only simplify, we have to actually solve for x, like we've been doing in the past 2 days. Once you get whatever sign is equal to, look for those values on the unit circle in between 0 and 2 pi, and you'll have your answers. Okay, so go ahead and try this one on your own. Try to solve for it, and then we'll check together. So a student asked a very good question about when we have to start adding 2 pi or subtracting 2 pi or adding pi or subtracting pi. And the answer really boils down to your interval. If on your interval you're going from 0 to 360 degrees, or in other words, from 0 to 2 pi, you're dealing with a unit circle. So it just wants those values that are restricted to your unit circle. If it goes from negative pi to pi, then it's not restricted to your unit circle, so you may have to subtract 2 pi in order to get the values that are within that particular interval. Or if it's from 0 to 4 pi, you're going to have to start adding 2 pi to get all the coterminal angles. Remember, coterminal angles start and end in the same place, so they have the same sine and cosine values. That's why we keep adding 2 pi or subtracting 2 pi until we reach the end point of our interval. It's also important, like I mentioned yesterday, to make sure to see if it's greater than or equal to or just greater than. Don't make the same mistake that I did yesterday in the notes. Double check. Now with this, a lot of students get stuck on the sine squared theta, cosine squared theta, and they always want to make it 1. And the problem with that is there are sometimes ways to make it 1 that are easy, and sometimes it's not easy or not possible. And when I see something like this, I think of a quadratic that's being squared, just because I know x squared plus x plus 1, right? So if that's my inclination, is I see something that can potentially be factored, it's often easier when you're looking at a problem like this to say, how can I get all the same terms? Because if you have a sine and then a cosine, it's like having an x and a y, and you don't want that, right? So if you're going to boil this down to a factoring problem, and sometimes there are multiple ways to do this, sometimes not, then you're going to want to get all sine values, right? In calculus, you're going to see that we're going to do something called U substitution. So this idea of substituting in order to simplify the problem in your head is absolutely essential for when we get to calculus. So let's turn everything into signs. Everything on the left side is a sign, except for I have a 1 there. And then on the right side, I'm going to turn that into 1 minus sine squared. Of course, I'm going to get everything onto one side and set it equal to 0 in order for me to factor, because I know that's how I factor things. So you get 2 sine squared x plus sine x. The ones cancel out, equals 0. Then you factor out your sine. Then you set each factor equal to 0. So sine x is equal to 0, or two sine x plus 1 is equal to 0. which means that sine x is equal to negative 1/2. So you look on your unit circle. All students take calc. And you look for all the values that either produce, all the radian measures that have a sign of 0 or that have a sign of a negative 1/2 on your unit circle. So it's easy to see the places in which sine is equal to 0. Where is sine equal to 0 on your unit circle? What's one place? Akil, where's one place?
Sorry, can you repeat the question?
Where does sine have a value of 0 on your unit circle? Think of your unit circle. Where is the sign 0? Nope. Pi over 2 is
Oh,
not
is it 0?
0.
Yeah, 0.
Where
pi
else?
and 2 pi.
0, pi, and 2 pi. Okay. Where on your unit circle does your sign have a value of negative 1/2? Yep. 7 pi over 6 and 11 pi over 6. So those are your answers. Questions? And because I have less than or equal to signs, I can include the 0 and I can include the 2 pi. Most of the time, what we've been doing leads up to this. This is a proof. Okay, whenever you see show that is your command term, right? And this was something that test in December that we had, almost everybody messed up because everyone assumed the right side and sort of had a cyclical mathematical argument. When it says show that, which you'll more often see than prove, then that means you do not